We worked on, well, first of all, we're Sam, that's me, Abu, and Abhinav. And we worked on extending random conic pursuit, which is a randomized algorithm for semi-definite programming. So you should all know what this is, but just in case you were sleeping, semi-definite programming is a powerful generalization of linear and quadratic programming. And they're generally of this form where we have convex constraints and objective and an additional constraint that X is positive semi-definite. So a lot of real-world problems can be put in this formalism. For example, metric learning, where we want to basically learn a kernel to match data we already have. Max cut is a pretty standard optimization problem, can be solved by semi-definite programming. And well, we don't solve it exactly, but it's relaxed into semi-definite programming, and we can get a pretty good approximation ratio. A few more that I won't go into too much detail, but sparse PCA, max variance unfolding, max eigenvalue minimization, QC-QP solving, logarithmic Chebyshev approximation, and a lot of combinatorial and non-convex problems can be not solved exactly, but relaxed into SDPs also.
So we are basically going to study extensions to random conic pursuit. Random conic pursuit was a paper by Kleiner et al. In 2009. And basically, the chief important thing about this paper is that it gets rid of the semi-definite constraint by construction. So you basically would be looking at generating rank 1 matrices which are PSD and taking conic combinations. You would never be bothered with the semi-definite constraint. So the algorithm, basically it starts with some feasible matrix x0, as most optimization problems do. We randomly draw a vector from a certain distribution. It really doesn't matter what distribution it is. It basically involves the previous iterate xt so basically it involves a mix of the previous iterate and the identity matrix. And from the normal, for which this is from the normal distribution, which is zero mean, and for which the variance is a mix of the previous iterate and a new rank 1 matrix, we draw a vector and compute a rank 1 update, not a rank 1 update, a rank 1 matrix XX transpose. And the semi-definite optimization problem, which was basically minimize f of x subject to g of x less than or equal to 0, and x is positive semi-definite, that basically now reduces to a minimization over the variables alpha and beta, and where alpha and beta are both greater than or equal to 0. And if we find that the objective has decreased, then we set the new iterate to the conic combination that we get from the optimization problem. In Kleiner, it is basically this optimization of alpha and beta is basically solved using a two-dimensional grid search. So can this algorithm be improved? One of the things that this algorithm does is it basically takes only one rank 1 matrix and takes a conic combination of the previous iterate and that rank 1 matrix. We considered the question of whether we can sample more than one rank 1 matrix and actually optimize over a conic combination of the previous iterate and all these rank 1 matrices. So our solution is basically sample multiple PSD matrices YTI and optimize over the conic combination alpha xt plus summation beta I YTI, and we feed this into a conic solver which is available in CVX OPT. And k equal to 1, which is basically just one rank 1 matrix, is a special case of the random conic pursuit. Now I'll have Abu take over.
So we want to use a real-world application to test our the RCP algorithm, the random conic pursuit algorithm, and our extensions to it, the extension where we search over multiple rank 1 updates, matrices. And one application is the sparse low-rank matrix decomposition. And we want to break a matrix down into a sparse and a low-rank component. So a matrix C, we want to find its components A and B here that minimize the given objective. It's gamma, which is a user-specified coefficient, times the L1 norm of A plus the nuclear norm or the trace norm of B. And so you can see from here that the L1 norm makes A, it sends A closer to the entries of A closer to 0. Therefore, A becomes more sparse. And B, the nuclear norm is a sum of the singular values. And so the sum of the singular values are sent closer to 0. And so a B becomes low rank as a result. And the parameter gamma corresponds to the desired level of sparsity. It's like a trade-off parameter between how much of a low rank versus how much of a sparse matrix component do you want. And this problem is also known as robust PCA. And so we can use this, this problem setup to construct synthetic data sets. Sure.
Is something missing in the notation? Why is A equal to B equal to 0, not the minimizer here?
Then they're optimizing over C equals to A plus B and C.
So there is a constraint.
That's the constraint, yes.
Yeah, it's after the last slice.
Okay.
There we go.
It should be written in the problem.
It should be write it in the constraint.
Okay, yeah. Subject to, okay. And so we can construct these synthetic data sets, and a really nice property of this problem is that we can control the difficulty of the problem we generate by just increasing the value of n, which is the matrix size. And in our experiments, we found that the parameter gamma has a very dramatic effect on the size of the feasible region, and which can allow some optimization algorithms to perform better than others, and some will perform very poorly as a result. And so this kind of corresponds to a stiffness parameter for the entire problem, where larger values of gamma will increase the stiffness of the entire problem. And so in conclusion, the sparse low-rank matrix decomposition is a really good way of getting a large range of different problem settings, which we can use to experiment with and evaluate our various optimization algorithms, specifically RCP in this project and the extension that we present. And so we're going to present results for 2 values of gamma, one relatively high, where it presents a very stiff problem setting, gamma equals 2, and one is much lower, gamma equals 0.001. And we want to see how our algorithm compares with our extension. Our RCP compares with the extension that we present for these different cases. So to read this, we also vary n here. N equals 5 in the top left, and going in row major order, and n equals 20, 40, 60, 80, 100. And the red line here shows the baseline RCP algorithm from Kleiner et al. And the different shades of the green indicate different values of k, which is the number of rank 1 matrices we're searching over in addition to the one baseline. And for gamma equals 2, you see that in some cases, our extensions do help, like for n equals 20, n equals 40. But in other cases, they don't, at least eventually for n equals 60, 80. And one possible reason for this is it could be due to luck. And so what we would like to do is run multiple times and get some sort of variance estimate of how much the convergence rates vary over multiple runs. But in all of these, notice that you see large punctuated drops. And this is mostly due to the fact that this problem is relatively stiff. And we found that this is a general problem with even the original Kleiner et al. RCP algorithm, where if you randomly select a rank 1 matrix that does not allow you to move in the feasible region, then you do nothing at that step. And so you see that for long stretches of time, you don't move at all because you just can't, you're not lucky enough to sample exactly in the right direction. Now for gamma equals 0.001, you see it's a little bit a different story. The baseline actually does consistently better than our extensions here. And part of the reason for that may be because that because the search, the search within the subproblem is slightly augmented. But I think further exploration is needed in our project to really find out why, for a not so difficult problem, because gamma equals 0.001 means that it's not very stiff, why the baseline does better than if you were to expand the internal search algorithm. Now here's a plot for gamma equals 2 again, but we're comparing the objective value after 100 seconds in this stochastic optimization. And the red is the baseline, and the different shades of green are different values of k, increasing from left to right, 2, 4, and 8. Number of rank 1 matrices we're using to search over. And the yellow here is the optimum that we found using an interior point method. And you can see at gamma equals 2, it's all of the algorithms, the baseline and our extensions, don't do very well in terms of finding the optimum. And that's because of the stiffness problem I mentioned earlier. You have to be lucky in selecting a random matrix that goes in exactly the right direction. And for gamma this large, that feasible region is very, very thin. So you have to be very, very lucky. And you can see for gamma equals 0.001, this is the exact same plot. But notice that we find the optimum pretty consistently, at least for low values of k. And beyond n equals 60, we weren't able to run the interior point algorithm due to the lack of computational resources. But our algorithm was able to recover what we expect to be the optimum as well for those cases. And this plot on your right side is the time it takes to reach a certain threshold objective. This is objective of 10. And so you can see that larger values of the k parameter consistently increase the computational time, the cost of reaching that threshold objective for this value of gamma. And so that's definitely something that we wish to explore more, and it's a potential for future work in terms of uncovering why this is going on. So just to recap, we saw that for large values of gamma, the stiffness becomes a big problem for not just our extension, but the original RCP algorithm from Kleiner et al. And one way to resolve that is possibly to consider the constraints and get some sort of make an informed decision about the direction you want to sample from, in trying to get a cone that overlaps with a feasible region sufficiently to give you at least a chance of moving instead of just staying in a single spot. And so this obviously is one potential future work. Another way to expand this potentially is to consider different distributions for f. The Kleiner et al. Paper suggested that the multivariate normal was a good general distribution, but that may not be the case. Maybe some problem-specific distributions will greatly accelerate the algorithm in those cases, such as this example. If we were if we more smartly picked the search direction, it could overcome the stiffness issue, for instance. And another possible extension, which we were able to include in our framework, but sadly did not experiment with, is to increase the rank of each matrix inside the conic combination. And this somehow augments the search problem. It would be interesting to explore how exactly the search is affected. And we can also use different algorithms. We used a cone LP solver from the package CVX OPT. The Klein et al. Paper used a bisection search because they only cared about 2 dimensions, whereas we cared about potentially higher than 2 dimensions because we have more than just 2 rank 1 matrices, or more than just 1 rank 1 matrix in combination with our current estimate. And that's it. Thank you. Any questions?
Just want to clarify, is this a solver for a general SDP? So any SDP you can plug in this solver and try to solve?
Yes, any SDP with convex objective and constraints.
Okay, cool. So I just feel that it's good to point that out because at least for IPCA, you have very fast solvers using like small IPCA.
Right.
How do you handle any convex cost?
We use in the CVX OPT package. We're not entirely sure how it augments the problem, but it somehow there's a method CP which allows you to specify a function as for the constraints and the objective, and as long as it's convex, it will try its best. Looking at the code, we saw that it somehow converts into a cone LP. But we're not exactly, I didn't look into the details to see exactly how it does that.
Because if function is non-linear, if you call it cone LP, the only non-linear constraint will be the membership in the cone. All other constraints will be linear.
Right, so it must do some sort of...
It means it can still be solved, and I was just wondering how, if you did anything.
We didn't do anything, we just used CVX OPT, the package, to solve it, yeah.
I think CVX converts all the problem in using
Yes, so I'm just saying if you have a non-linear objective, to turn it into a true SDP can lead to huge drop in the number of variables, at least if you just follow the black box CVX style of doing things. And that's really painful. So you have to be a little careful about handling non-linear functions when doing SDPs.
Right.
So it basically asked us to provide the F values, the DF values, and the Hessian values. So we had to, the function has to provide all of these values to the solver at any iteration. So I think that was enough for the solver. It basically, it did not, I think it did a convex relaxation, convex quadratic relaxation. It was good with that, along with the SDP constraint.
Means when trying to scale up an optimization method, one thing that you would usually not try is to use a black box solver. Because the speed ups that you might provide by doing your randomness, they could be killed by using a black box solver. So in some sense, those two are usually in conflict with each other. But it's fine, means solving large STPs is anyways non-trivial, so I don't expect you to also write the solver. But it's good to keep in mind that whenever you're trying to speed up, you'll have to try to build the whole system yourself.
Right. I'd like to note that for our sparse low-rank matrix decomposition, I think it was the objective constraints were all linear. The Hessian was all zeros. We returned zeros to the CVX OPT solver.
And you are saying one of the future directions is to have a smarter way to sample the directions.
Exactly.
To search for. Wouldn't that seems to be similar to the probabilistic optimization that Sylvia talked about yesterday?
Oh yeah.
They use a Bayesian type of updates.
Well, you start entering a lot of non-linear program in the sense that even if you don't want to do full Bayesian, based on you cannot really think about creating a smarter direction without carefully looking at what your function looks like, right? So by building a good model of a function and then using that to guide your direction selection. And so
Right. Yeah, that was somewhere in the lines of maybe altering the prior or adding a prior for the random distribution of the vector that we use to create the rank 1 matrix. But if we have a specific problem, taking advantage of the structure of that specific problem could definitely provide a much better.
Is there any theory also here which helps us characterize the solutions obtained by this randomness, or there is no theory which analyzes how good a random your problem solution is for the original problem?
I don't remember if the original paper. I know it's not. I don't think they did it for the general case the general formulation they presented, which was just convex objective.
Well, I'm asking
right?
in your case, did you guys?
Oh no, in our case, I don't think so.
There is a paper that does something intelligent about choosing the maximum, an eigenvector with the maximum eigenvalue over the previous iterates. That is that actually builds on this work. That was the only work we found that did something intelligent for the sampling.
No, I'm just asking, did you prove any
No.
theorem in your project?
No,
we didn't. Yes.
So when you try to find the conic coefficients of the random factors, do you still need to rewrite the trace?
No, we optimize over the dual, and so dual just consists of a L1 norm summed with a trace. Yeah.
So the other question is, what is the benefit of consider randomly joined instead of doing the greedy approach?
Instead of doing what? Say again. Sorry.
Doing the greedy approach, obviously you compute the gradient and then compute the maximum single factor. That's like French warfare.
So you're saying, what is the benefit of this over, say, a gradient algorithm?
Yeah. Yes. Instead of joining random one factor, you're now trying to find a particular random one factor based on the gradient of that function. So what are the differences? Is there any advantage of one of them?
I don't think so. We should have done that. We did not, because we actually expected the function to return the function value, the gradient, and the Hessian. So gradient descent was one of the easiest things that we could have compared with, but unfortunately we did not. We did not do a comparison.
That's a good question. I'm wondering how well it would do in the cases, say, that Kleiner et al. Explores in their paper in comparison to their method. So I'm not sure, but that's interesting.
I mean, this is always a valid question. Whatever method you do, you better compare it against subgradient.
Yeah.
Because getting subgradients is usually one of the cheapest things.
Right.
Yeah, but anyhow, means you don't have to compare against everything, but it's good to know whenever implementing a new optimization procedure. If it's in general, your problems were non-differentiable, but as a sanity test, it's good to always compare against a version of subgradient.
I see.
Most of the time you might get lucky and that subgradient guy might suck, but sometimes actually doesn't suck, especially for large STPs, at least in my experience. So it's always good as a sanity test to try it out.
I see.
And of course, if it is good, then you can come back and say that, okay, then I'm just stochastic subgradient. Anyhow, so I hope you're keeping track of the time. We shouldn't run too much over.
Yeah, they are on time.
Okay.
The questions and answers slightly over time.
Okay.